going to proceed with our next speaker. And he did a long trip. He's coming from US, from Washington. He says that he's semi-retired, but I don't see a retired person here. And he's a software development consultant with 38 years of professional experience. So maybe he started when he was like in kindergarten. And he has experience in a wide variety of languages, systems, frameworks, and domain. And his main focus lately is to spread the gospel of quality. So he has come here to preach, I think. So let us welcome on stage Dave Aronson with his talk.
Welcome.
Tight Genes, Intro to Genetic Algorithms.
Okay, just a moment. Need to put the presentation over on the correct screen. There we go. Okay, Yasas Athena. Wait, there's more. Imeo Dave Aronson, o T-Rex tu Codosaurus, que petaxe do metocatokidio pterodactylo yanasas mathos geneticos algoritmos. Alla Tatocano sta Anglica. Mainly because you just heard almost all the Greek I speak. There we go. So what are genetic algorithms in the first place? They are optimization heuristics, which is fancy talk for shortcuts to find a solution to a problem. Ideally, the best solution, but we'll usually have to settle for something good enough due to constraints like time and money, which is why we generally use a heuristic in the first place. There are lots and lots of kinds of optimization heuristics, but genetic algorithms in particular are inspired by real-world biological evolution, in particular the principles of survival of the fittest, combination of old sets of genes, no, not like these, into new ones, and random mutation. The history goes back to about 1950, when Alan Turing, as in Turing test, Turing machine, and Martina Tomaidu's slides earlier, you might have seen him mentioned on there, he proposed a learning machine in which he figured the mechanism of learning would be similar to biological evolution. Nothing much ever really came of that, and it took a few decades for genetic algorithms in general to gain much traction. But in the late 1980s, the first actual product based on genetic algorithms, a toolkit for industrial processes, came out, published by General Electric. These days, MATLAB and similar tools usually have facilities for genetic algorithms built in, and many programming languages have one or more libraries available for genetic algorithms. But the actual usages of genetic algorithms still remains mostly obscure and honestly boring, used internally by companies in their industrial processes and scheduling and logistics and so forth. But once in a while, they do get used for something a little more interesting and more publicly known. For instance, in 2005, NASA used a genetic algorithm to design its antenna for the ST-5 series of satellites launched in 2006. No, that's not just a paperclip that got bent up by somebody fidgeting in a boring meeting. The NASA Jet Propulsion Laboratory website says, its unusual shape is expected because most human antenna designers would never think of such a design. And that's actually one of the great strengths of this approach. But how do genetic algorithms actually work? Now, most people hear the name and think, oh, that must be really hairy and complicated. But no, it's really just a simple series of steps. First, we create an initial population of candidates. In genetic algorithm terms, these are usually called chromosomes, but since each and every living being has lots and lots of chromosomes in each and every living cell, well, I don't like that term. I think it just leads to confusion. So I just call them candidates or solutions or something like that. The next step is to assess how fit each of these candidates are according to whatever criteria we want to apply. We do it at this step mainly because the information is used in the next step, which is to ask, are we there yet? Or are we done? That's usually based on the fitness, but could be based on other criteria or a combination. If we're not done, and we're usually not done on the very first run through, then we pick some candidates out of that pool to use in breeding the next generation. And this is also usually based on the fitness to simulate survival of the fittest. And after that, we, of course, use those candidates to actually breed the next population of candidates. And next is an unusual step, which is to mutate them for more diversity in the gene pool. And finally, we go back to step number 2, which is to assess how fit this new population of candidates is, each one. And this sequence could be represented at a high level in some fairly simple code like this. Now, this happens to be in Ruby because it reads fairly close to just plain English. So even those of you who don't know Ruby, I'm confident you'll understand the ideas and be able to follow along with the code. Now let's take a closer look at each step by working through some examples. First, we create an initial population of candidates, but what is a candidate and how do we create one? There are lots of different things they could be, but in the general category, they are solutions to some particular problem, usually represented as instances of the same data type, which could be any data type we really want to deal with. The simplest kind is a simple string of bits, and this will do fine for questions that consist of a simple series of yes-no questions. And that may sound simplistic, but there is a huge category of problems that boil down to this, called knapsack problems. The canonical example is that you have a knapsack, or whatever you call it, and many things you want to put in it. So you want to find the combination of items that will fit in the backpack and has the maximum possible value for whatever definition of value you're applying. Let's look at a concrete example. Suppose we know a farmer who has a smallish truck, and he needs to decide what to take to the farmer's market every weekend. And on this farm, he has some cows. E-I-E-I-O. So among the things he can take are cows, of course, milk, cheese, butter, ice cream, meat, and leather. My apologies to any vegans out there. His truck actually has room to take all those items, but it can only handle so much weight, so that's going to be our constraint. His choices are as follows. You don't need to read or memorize all that. Just notice that it totals up to 8,600 pounds. However, his truck's suspension can only handle 4,000 pounds. In other words, 2 tons in US units. Let's see what happens if we use a genetic algorithm to determine a good enough truckload. First, we need a way to represent each potential solution. And in code, we could write a class like this. Oh, we're just making a random number. How's that represent the choices? We're making a random number with 7 bits. So we have a random 1 or 0 for each of our choices of do we take this item or not. We could get as complex as we want in this, like determining a minimum or maximum number of items, but as I'll say about many of the further functions. I'm just going to keep it simple. Now, to create an initial population, we could just create a bunch of these candidates and stuff them into an array or a vector or list or whatever, like so. And this could actually be done in much more idiomatic Ruby, so those who know Ruby, don't scold me for that. I'm just trying to keep it very understandable by those who don't know Ruby. So if we create an initial population of 10 truckloads, we might wind up with something like this. And we can get those yes-no decisions by iterating over the items and seeing if the corresponding bit is on in the number. Next, we assess how fit each of these candidates are, and we do this with what's called a fitness function. Surprise! In this case, we already know we want the actual cache value and total that up for the whole truckload. But any load that's too heavy for the truck is totally worthless. And in Ruby, that would look like this. We decode which items we want to take, sum up their weights. If that's more than the truck's capacity, we return 0, else we sum up their values. And again, we could get as complex as we want in this function, and NASA's antenna fitness function certainly must have been. If we run this against our current population and sort on fitness descending just to make it easier to envision what's the best ones, we get this. So now that we've assessed their fitness, we ask, are we done? But what are our criteria? This function can be simple, but it can take some thinking to figure out exactly what it should do. With a knapsack problem, a good solution, even the absolute best possible solution, can be made totally worthless by adding just one more wafer thin item and thereby exceeding the constraints. So what we're going to do is record the best we've seen and stop if we haven't seen anything better within 100 generations. In Ruby, that would look like this. When this code is initially run to define the function, we set the initial best combination as totally empty, because we know anything's going to be better than that. And we set how many generations since we've seen it as 0. And when the function is called, we increment the generation counter, look at the fitness of the current candidates, and select the ones better than our current benchmark. If there are any, then we set the fittest one as our new benchmark, reset the generation counter, and return false, meaning, no, we're not done yet. Else, if there are none, if we have hit 100 generations, yay, we're finally done. Otherwise, no, we're not. Once again, we can get as complex as we want in this function. Not only in checking the maximum fitness, we could check the average fitness, or other stopping criteria like a maximum amount of time, or number of generations, or all kinds of other things, or let the user press a stop button, or any combination of those. Now, assuming we're not done, then the next step is to select some candidates to breed the next generation. And the obvious way, that's what's usually used, is to take the top 2, like so. You take the population, sort them by fitness descending if we didn't already, and just take the top 2. And with our current population, that would get us these 2 choices at 20,000 and 14,800 of whatever units we're counting them in. Now that we've chosen our breeders, we actually breed them. And the usual way to do this is called crossover. And that consists of taking the data points, or in genetic algorithms terms, the genes, hence the name, from one parent up to some randomly chosen crossover point, usually different for each candidate, and then switch to the other parent. And in Ruby, that could look like this. We establish the crossover point as a random number from 0 to however many items there are. Then we iterate through the list of items, and if we haven't hit the crossover point yet, we get that decision from the first parent, else the second parent. And if we do this once with a crossover point of 3, we get this. But this is just one of 10 results because we're making a whole new population, like so. And you might notice this is very much like how we created the initial population, except that instead of each candidate being made from scratch, it is the product of breeding our two chosen breeders. The whole new population might look like this. Lots of family resemblance there, huh? None of these loads include a cow or butter or leather, and they all include cheese. That's because both of our two breeders were like that. If we were to just continue breeding the best of these generations, we wouldn't ever see any loads including a cow, butter, leather, or no cheese. But we fix that in the next step, which is to mutate them. Again, I'm going to keep it very simple and just give each gene a 1 in 4 chance of flipping. And in code, that would look like this. We go through the item numbers, and for each one, if a random number from 0 to 3 is a 0, we flip that bit. And as usual, we could get as complex as we want here, like having some genes more likely to flip than others, or having some minimum or maximum number of mutations, or all kinds of other options. If we run this on our current population, then we might wind up with something like this, where the green color indicates that it changed. You can see that we now do have some truckloads that include a cow or butter or leather or no cheese. And now we go back to step 2, now that we have finalized the state of the current population, and assess how fit these actually are. That would give us this chart. Oh no, our maximum fitness actually went down from 20,000 to 15,000. But don't worry, as you may recall from our "are we done yet" step, we just hang on to the best we've seen and just try to outdo it. We haven't lost it. The next generation might look like this, a slight improvement over our original best, from 20,000 up now to 20,800. So we set that top one as our new benchmark. We set our generation counter and just keep going. If we let this run to completion, we might wind up with something like this, with a truckload scoring 26,000, a significant improvement made up of cheese, meat, and leather. So that's one complete run of a genetic algorithm. If we wanted to see if this was the best that this could do, we could just run it again. The whole point of it is that it's so much faster than brute forcing the entire solution space, or in some cases, precise calculation. Okay, maybe when we only have 7 items for 1 truckload a week and such simple criteria, actually writing all this code might not be faster. But for more items and more complicated criteria, yes, it may well be worth it. Now suppose we want to evolve something completely different. Suppose we want to evolve a set of character statistics for a Dungeons & Dragons fighter character. So now our candidates will be tuples, or if you prefer, tuples, of numbers, rather than strings of bits. Dungeons & Dragons character stats are strength, intelligence, dexterity, constitution, wisdom, and charisma, each determined by rolling 3 6-sided dice, or 3d6 for short. And I'm going to gloss over how you can sometimes have extra strength. No, you can't in this simplified example. In Ruby, that might look like this, with the roll function being left as an exercise. The initial population might look something like this. So, how fit are these as fighters? We have to assess them, but what are our criteria? We're trying to evolve fighter characters, so it's going to be mostly based on the strength, the constitution, and to some extent the dexterity. The intelligence and wisdom and charisma, not so much, but we don't want them too low because of occasional saving throws. I tried several different fitness functions, such as totaling up twice the strength and the constitution and half the dexterity, and just ignoring the others, but the others tended to get very low. And even the dexterity wasn't doing very well. So I tried prioritizing them, just linearly, adding up 6 times the strength, 5 times the constitution, and so on, down to 1 times the charisma. But then the other stats got a little too high. The character seemed a little too generalized rather than, oh, that's clearly a fighter character. So I finally settled on prioritizing them much more strongly with a geometric progression rather than linear, totaling up 32 times the strength and 16 times the dexterity and so on down. The point is that even though the fitness function may be very simple, it can be very difficult to figure out exactly what it should do for best results, for whatever value of best results you care to apply. If we run this on our current population, we would get this. And now that we've assessed their fitness, we can ask, are we done? But what are our criteria for being done? Let's say we're done if any character scores at least 90% of the maximum total score of our fitness function. I'll spare you the math, but that would be 1,021. And in code, checking that would look like this. Very simple. None of our current candidates score anywhere near 1,021, so next we select some breeders. And taking the top 2 scorers, again, we get these 2. And then, of course, we actually breed them, but how? This time I want to use a slightly different strategy of essentially flipping a coin, or as we used to say, rolling a D2 for each gene, like so. We go through them, flip a coin, and see which parent we get that particular stat from. And that might get us a result like this. But again, this is just one of 10 results because we're making a whole new population, which might look something like this. And there are 2 main things to notice here. First, the number of red and green, denoting which parent it came from, is not always the same, neither in a particular individual nor the entire population. It's a series of random coin flips, so it could be up to 6 to 0 either way, and it'll average out to about 3 and 3, but it could be anything. Second, once again, notice the family resemblance. For each of these stats, there are only 2 possible values. Or in genetic algorithm terms, for each of these genes, there are only 2 possible alleles. Even though we're no longer using simple yes-no decisions, there are only 2 possible values because it had to be either the one from the first parent or the one from the other parent. And if those were the same, then there would be half as many possible combinations. We could have up to 64 different combinations, the way it is now, but if 2 were the same between the 2 parents, that would chop it down to 32. Oh, yes, there we go. At a glance, these look much more suitable as fighters than our previous generation. And we'll calculate their actual fitness later. But once again, if we were to only keep breeding the fittest of this generation and the next and so on, we would never see any change in those possible values. We'd be stuck with just those 64. But again, we mutate them to get a little more diversity. And once again, I'm going to keep it very simple and give each gene just a 1 in 3 chance of staying the same or going up a point or down a point within the valid range. And in code, that could look like this. For each stat, we basically add a random number from -1 to 1 and clamp it within the valid range. And as usual, we could get as complex as we want. We could do things like make it more likely to go up or down if it was already very low or very high, possibly doing so by multiple points, and lots of other options. If we ran this on our current population, we might wind up with something like this, where the green means it went up and the red means it went down. As you can see, it's now much more diverse if you look at the number of different values in any particular column. So now we go back to assessing how fit these new candidates are, and we get this result. So now we can see that, yes, they are indeed much more fit to be fighters than the prior one. The previous generation ranged from 476 to 760, and this is from 635 to 851. It's still nowhere near our stopping criteria of 1,021, so fast forwarding through 6 more rounds, we finally get one suitable character with the maximum 18 strength and constitution and acceptable, though subpar, dexterity, and surprisingly high intelligence. Go figure. That's not a problem, just a bit of a waste. If we wanted the characters more specialized, we could make the fitness function more complicated by doing things like demanding that the class's relevant stats be well above average and forbidding the others from being so high, or at least applying some sort of moderating penalty. So now we've evolved a set of fighter stats. Suppose we don't need any more fighters, but we'd like to have a wizard. All we need to do is tweak our fitness function like so, to prioritize first intelligence, then wisdom, dexterity, and so on, down to strength. A new initial population would look more or less the same, since we haven't changed how that's generated. So I'll skip that, but fast forwarding, after 11 generations, I wound up with this: 3 characters, at least 90% fit to be wizards. And they're mostly pretty good in the other stats, but not so much as to be obviously better suited for some typical class, though that top one looks like a bard to me. There are many, many other ways we can use genetic algorithms. They can create images, music, even code, possibly a code editor like Scott Chekon alluded to this morning. And I'm now working on a system to use it to schedule conference talks. So think about it, and you might be able to use it for something. And to recap what you've learned here today, genetic algorithms are optimization heuristics, which is fancy talk for shortcuts to find good enough solutions to a problem. They're simpler than you probably thought. They can use very simple functions, but it can be a little tricky to figure out exactly what those functions should do for best results. And this approach is applicable to a huge variety of problems, including many complex enough that a semi-random algorithm can come up with great solutions that we mere humans would never think of. Now, if you have any questions, of course we have some time for that now, and there's my contact information and the link for the repo. This uses Reveal.js, so it's a little more setup, but if you just want the slides, they're at that URL, complete with a script, which I've mostly stuck to. So let's have the questions.
That's great. Excellent speech. Thank you so much. Let's see what questions do we have. Do we have any questions from the audience? Okay, here we go. So the first one, where can genetic algorithms be applied? What problems do they solve?
Well, they can be applied primarily anywhere where the solution you're looking for is easily described in some form of ideally relatively simple data. For instance, if it can be described as a string of yeses and nos, or true, false, 1, 0, whatever, that's great. Well, at least that passes that hurdle. The other criteria I can think of offhand are that you need to be able to create these candidates reasonably simply. And the hard part is you got to figure out some way to evaluate how good a solution is. For instance, I mentioned I'm using it right now to evaluate conference talks and evaluate conference schedules, given a list of talks and how many days, rooms, and speaking slots there are. So I'm in discussion with some organizers about what they consider to be good or bad about a conference schedule. Like, well, obviously you don't want any speakers to be scheduled for 2 rooms at the same time, And there are things that make a schedule better, like having a wide variety of topics and levels of expertise required during a given time slot or throughout the whole day.
Thank you so much.
Okay, good. So the next question is, okay, what do we need, okay, to be able to find useful solutions? A standard laptop or like, okay, something more like bigger, like a cloud computer or something?
Oh, well, this is simple enough to do on an ordinary laptop. This is a 2020 MacBook Air, M1, so late 2020.
And?
But any reasonable computer would do. Even the old second-hand ones should do fine. It's all a matter of, well, your population size, for one thing, that will generally be held in memory, and how efficiently you can evaluate their fitness and so forth.
Okay, great.
Yeah, we'll have another one.
And we have another one? Yes. Okay, so are there example fitness functions available for different software qualities, abilities? Do you use this when spreading the gospel of quality? Wow.
Interesting question. I don't know of any offhand that are commonly used for evaluating the various abilities of code that you're trying to evolve, which is a fairly complex question in the first place. One obvious one that springs to mind would be to benchmark the runtime efficiency of various algorithms, just to make sure you have a timeout on it in case you create an infinite loop. There may be some academic literature on that particular topic that you can go read, but I haven't. Oh well.
Okay. So the next, are these examples of fitness functions available for different software qualities? Do you see this when spreading the gospel of quality?
Isn't that what he just asked?
No, this is the...
Okay. Do you have any favorite open source libraries to recommend for novices to get started?
Well, I took a look at some of the libraries used in some of the languages I use, which these days would mostly be Elixir, Ruby, Python, C, and JavaScript. And most of the libraries I saw, honestly, if you're just getting started in genetic algorithms, it might be easier to just roll your own from scratch rather than try to understand what some of the terminology they mean, the terminology they use means, and try to figure out what would, which particular option to pass in would best fit what you're trying to do. If you're doing the whole thing from scratch, of course, it's going to fit your purpose much better, and it'll also help you learn genetic algorithms much more deeply.
Okay.
Great. Do we have time for
Yeah,
one more
we'll
question,
have one.
I guess?
We'll have time for the last one.
Okay, so most practical applications that as a normie developer I am likely to face and find this useful for?
That's somewhat of a gotcha question, because frankly, most of us are unlikely to ever actually need to use genetic algorithms. Those who are in a more engineering type of endeavor, where you might be doing something like, say, designing an antenna, might find this useful. Most of us, we might find some hobby usage, like my conference scheduler thing. But the actual applications in the business world tend to be, so far, boring interior business things like industrial processes, logistics, and scheduling. So, oh well.
Okay, great.
Great.
Thank you very much.
Thank you very much.
Thank you.
Excellent speech.
This is something from us.
Thank you.
Είσαι φοβερός ομιλητής. Can you say that? Είσαι
Ise,
φοβερός
foveros,
ομιλητής.
Homilitis.
You are an amazing speaker. Thank you so much.
Thank you.
Obrigado.